All right, welcome back to the third video in week one of Physics 325, Optics. In this last video, we basically ground through Maxwell's equations, found out what they meant, and used them to show that there exists electromagnetic waves, namely that there is a wave equation implied by Maxwell's equations. And we learned a few things about that wave equation. Today we're going to zero in on perhaps the most important way of looking at those waves, the most important solution to the wave equation, namely the electromagnetic plane wave. The reason it's so important we'll see later in the course, but it has to do with the fact that the plane wave is like the fundamental basis that we can derive every other image off of. Just like you may have heard that we can make any arbitrary shape, for example, in time, by adding up a bunch of sine waves. This is called Fourier series and Fourier analysis. We can make any two-dimensional pattern that we might see in a wall in terms of their constituent plane waves. So they are the kind of the fundamental building blocks to things like images. It's very important that we understand plane waves because we can make any other wave from them. All right, so let's recap. We had the wave equation here, and we are looking at solutions to this. Now, the three-dimensional wave equation is complicated. There's 9 dimensions in space we have to worry about: x, y, z, bx, by, bz, ex, ey, ez. It's a lot to take care of. So we're going to start slow, and we'll look at the properties and the corresponding plane waves that come about with the one-dimensional wave equation. All right, so we just, instead of having a gradient, we just have a derivative with respect to z. And last time we found out that in order to satisfy this wave equation, this E of z and t here had to be of a specific form, namely that z and t were related through one variable, z minus, plus or minus really, c times t. Okay, so given that, the simplest solution we might find for that is a sinusoid. We saw a picture of that. So our first guess would be, we know that the variables z and t must be related in this particular way. Let's just throw it directly in there. But that's a problem. We have a cosine. We can't just throw something that has units in. Z minus ct has units of meters, right? We can't have the cosine of something with meters. I mean, cosine has a power series, so that would mean it was equal to meters plus meters cubed plus meters to the fifth. Makes no sense. So we have to fix this up somehow. And the way we can do that is we can look at this variable and we can rearrange it a certain way. So the argument, by the way, I don't know if you've heard the terminology, the argument of a cosine of a trigonometric function like this, we call a phase often. Okay, so we have our z minus ct. And we need to somehow convert that into something that is unitless. This has units of meters. Let's multiply the whole thing with something, some constant k, that has units of inverse meters. And then it is a valid argument to a cosine. So we'll multiply it by k. We'll multiply by k, which has units of inverse meters. And when we multiply this whole thing by k, then it's a valid phase. So it will become kz minus ck times t. And that is going to be the input to our cosine. And now we have something that makes sense. We haven't interpreted what this k is. We just know that it has to be there in order to be a valid argument to the cosine here. So we'll do that, and this is what we wind up with. We have a cosine wave here. And because it satisfies the wave equation, we can just watch it propagate, and it'll do something like this. Not too exciting, right? Our one-dimensional wave equation is just moving in a constant speed in the z direction here. All right, let's do a bit of work, though. Let's figure out what this k actually means. So what we're going to do is we're just going to freeze time, and this is what we see, right? We have this pattern here, and we can look at the distance between the peaks. So for example, we can freeze at any time. That would be an overall phase, and why not just let it equal 0? So we're going to look at cosine of kz here at time t equals 0. That's what this function looks like for all space. And we can see we have this argument here, and the spacing between it, we're going to call that lambda. That's the wavelength, okay? So we have, whenever this thing is equal to 2 pi, it repeats itself, right? So the spacing between the maxima is when it repeats itself. So we have k times lambda is equal to 2 pi, right? So in general, k times z is the phase. Now we want k times lambda is equal to 2 pi. That is, by definition, the distance over which it repeats itself. Or, the way we can write this, we can write k in terms of this wavelength, the separation between constant phases, 2 pi over lambda. All right? And we're actually going to call it something. We're going to call it the wave number. So when we do this, we have our wavelength lambda, the distance between repeating points on that cosine curve or sine curve, and the wave number, which is just 2 pi over that lambda. It's kind of like the spatial frequency, right? That's another way we're going to look at it. But we'll get to that much later in the course. For now, let's just know that there's this thing called k, and we can actually interpret that. Okay? So we have now, we know what that k actually is. That k is 2 pi over lambda. So we can even write it. Cosine of 2 pi, actually I'm going to do it this way, of 2 pi times z over lambda minus ct, ck times t. And this tells us that whenever z goes a distance lambda, we acquire 2 pi more phase. All right, that's what this is actually telling us. So let's go further. Let's try to interpret this term here in front of time. Okay, so what we're going to do is something similar that we did before. Now we're going to freeze a location, right? We'll look at, say, z is equal to 0. And look what the field is actually doing at that point. So the field is going to be moving up and down and up and down. And we can plot that direction, the field. And we can plot what the electric field is doing for all times. So we can do that. We can see what's going on the bottom here. And if we plot versus time, we're also going to get a sine wave, right? And we're going to do a similar trick. Let's just try to interpret this. Now we're plotting versus time. And we have a wave like this. The distance not in space, but at a fixed space in time. Well, we call that the period, right? And the period is equal to 1 over the frequency of the wave. Right? This is just the distance that it takes to go 2 pi radians. So we'll have cosine of negative, it's cos of negative x is cos of x, but we'll just keep it. So that is going to be our new wave. And at time t, capital T, the period, this is going to be equal to 2 pi. So ck times t is equal to 2 pi, right? So ck is going to be equal to 2 pi divided by the period. 1 over the period is what we call the frequency for a wave, 2 pi f. And that's what we call omega, right? The angular frequency. So we can do one more. We can kind of one up our wave here. And we have cosine, which is our solution, of kz minus omega times t. And that is our one-dimensional plane wave. Okay? So it's going to look like this. So we have a angular frequency. We have omega, the angular frequency, which is related to the wave number via ck is equal to omega. And also k is equal to 2 pi over lambda. Okay? So we can now write our wave equation, our solution to the wave equation this way. We can write it as a cosine. Oftentimes in the course, we're going to write this as a complex number. It's just going to be much more convenient, right? And remember, this all comes from this formula. This might be a review for you. If not, we're just going to use this quite a lot in the course. E to the I x is equal to cosine x plus I times sine of x. That's Euler's formula. Okay, and we're going to use that a lot for x is equal to kz minus omega t. Okay, we're still in one dimension. I've been going on about how complicated 3 dimensions are. So let's move to the 3rd dimension. And it turns out we just need to make a very simple modification. Right? We're moving in one direction. We're moving in the z direction here. And we need to generalize that kz to moving in an arbitrary direction. And to move in an arbitrary direction, we're just going to put a little hat on it. Okay? So what we're going to do is we're going to say kz in 1D is now going to be some vector k dot r, right? And k is equal to kx, ky, and kz, like that. And r, of course, is just going to be x, y, z. x, y, z. Okay, so that's all we're going to do to move to 3D. We're now going to have a wave vector instead of a wave number, and it's going to be pointing in some direction. Now it's still going to be the way. If you notice, if we had k was just in the z direction to begin with, is equal to k naught, let's say kz to begin with. In other words, I can write it like that, 0, 0, k. Then k dot r, in this case, is going to be kz. And that's exactly what we had before. So it's going to be the exact same analysis, except it's now moving in the k direction instead of the z direction for one dimension. So it's just moving in some arbitrary direction, but along that direction, it's the exact same thing we just saw. Instead of moving in, say, we call this z, instead of moving in the z direction, it's going to be moving in some arbitrary direction this way, but it's still going to be this cosine wave. Okay, and we still have the relationship that the magnitude of k is 2 pi over lambda. C times the magnitude of k is equal to omega. Okay, so our three-dimensional plane wave is going to be almost the same thing. It's just now going to be with a different argument for the phase. Okay, so it may be confusing at first. Why do we call this a plane wave? I know it was to me when I first learned it. So let's figure out why we call this thing a plane wave. Okay, we have this k dot r minus omega t. So if we remember, the argument of a cosine is called a phase. Okay, so what we're going to do is we're going to look at a surface. We're going to look at a surface of constant phase. In other words, we're just going to set that stuff in the cosine to a constant, 12 or c naught or something like that. And we'll look at the condition, the equation for that phase to be constant. Okay, we can write it this way. So really what we're doing here, say we take a snapshot at time t is equal to pi or 12 or 0 or 10 to the 17 seconds. It doesn't matter. It's a constant. So t is equal to some t naught. Then our phase, k dot r minus omega t naught. This is omega t naught is just a constant. So it's just going to be like this. We'll get this over to the other side. Constant plus a constant is a constant. So k dot r is equal to some other constant. This is a weird equation. K dot r is equal to a constant. If we write it out, it says kx times x plus ky times y plus kz times z is equal to that constant. All right. And this actually, as it turns out, is the equation in 3 dimensions of a plane. Okay. Why is that? Well, imagine we looked at z equals 0. We'll call this x, y, z here. X, y, z. Let's look at z is equal to 0. We'll block it out. Well, this is just like a y equals mx plus b equation, right? This is a straight line in the xy plane. We can look at the y equals 0 plane, a straight line in the xz plane. And we can look at x equals 0, another straight line in the yz plane. And that kind of defines the plane here. Now this might ring some bells or some unearthed nightmares from Math 200 or wherever that course is called now that you learn this in. But this is the equation for a plane, and it's normal. It's normal to the vector k. Here, this is just the equation of a plane. And this is what it looks like as per my plot that I took off Wikipedia. Okay. So this is what a plane wave really is. The phases, it's like a cosine moving up and down. But if we look at a constant phase, if this is my k vector here, it says that the phase is constant in a plane perpendicular to that phase vector, right? And that constant phase, say a peak of the sine wave or the cosine wave, is traveling at the speed of light. So this is what a plane wave is. Imagine this, I had an infinite book here. It is a plane that went in every direction, perpendicular to this vector, to this k vector here. A plane wave just moves at the speed of light that way. And it's just moving at a constant speed. Now, it repeats itself. Lambda behind, there's another vector, so it's going like this way. So basically, a plane wave describes surfaces of constant phase moving at the speed of light along k. So what do we have so far? We have this plane wave. And we figured out the argument of that cosine or that complex exponential there. We have a surface of constant phase moving at the speed of light. So given k, anywhere along that plane perpendicular to it at a fixed time, we have the electric field is an arrow pointing in the same direction. And as time increases, that plane just moves at the speed of light. Okay, but what about this electric field, E naught here? Okay, what can we say about that? Well, in your assignment, in assignment 1, you're going to do a bit of math. It's not too hard, I promise. This is our first clue. This constrains the form. Given this k here in the exponential, that tells us the electric field is constrained in some way. We can make it a bit more rigorous by looking at Maxwell's equation and finding out that the divergence of E in free space, like we are currently working, is 0. Okay? So we have the divergence of E is equal to 0, and that's equal to k dot E. So if the dot product of two vectors, is 0, that means they're perpendicular, right? What do you know? If we look at this, we have directly, falling out of the math, that we have a plane wave, and it doesn't tell us exactly what E is, but it says whatever it is, it's perpendicular to k. It's along that plane of constant phase. So we have that E is perpendicular to k. In other words, light is transverse. So we now know that light is transverse. We figured out quite a lot. So to hammer home the point, suppose that we're moving along Z. Now E, we don't know exactly what it's doing, but it's wiggling back and forth along some direction in the xy plane. We have 2 degrees of freedom for the electric field oscillations given k. There's a fancy name for that. That is the polarization of light. You'll hear about that in Lab 10, I believe it is, as well as Week 9 of this course. We're really going to dig into polarization, but this is where it comes from. Given k, we have 2 degrees of freedom, so we can be, for example, horizontally polarized or vertically polarized, or we can sum up a few different waves and be anything in between. We can even be circularly polarized. So this 2 degrees of freedom leads to interesting optical phenomena, but right now we just know that it's perpendicular to k. This is a very important point, and so we'll get back to that later in the course. There's one more thing I want to say that we can kind of glean from plane waves here. We can look at the magnetic field. Okay, so what about the magnetic field given this form of the electric field that we just found? All right. So Maxwell's equations. We have another Maxwell equation. We know that the curl of E, what does Maxwell tell us? That the curl of E is negative dB by dt. Okay? And what we're going to do is, let's just make our lives a tiny bit simpler. Let's let k be in the z direction, and E is in the xy plane. We'll just call that direction x, is E naught x. Okay? So that E is equal to E naught e to the I kz minus omega t, 0, 0. So that's our electric field vector here. Okay, so that is what the electric field is here. And the magnetic field is some vector. We don't know yet. So let's try to figure out what that electric field, what that magnetic field actually is. Okay, I can say a bit more for it. I can say that whatever it is, the partial derivative of it, negative partial derivative of it, is going to be the curl of E. Okay, so that's going to be dx. This is how we do the curl. This funny rule. You can calculate the curl this way. And this is going to be E naught e to the I kz minus omega t, the x component, and the rest are going to be zeros. Okay? So let's have a look at this. If we look at the x component, it's going to be 0. The z component, it's going to be 0 too, because we have time derivative of 0, and there's no y dependence. There's no y dependence here, so this derivative is going to be 0. The only thing that's not 0 is going to be the y component, which is going to be time derivative d by dz of E, let's say 0. So let's bring it back down here so that I have the time derivative of E naught e to the I kz minus omega t and that's equal to I times k times E naught e to the I kz minus omega t. Should probably come up with a shorter symbol for that. That's going to be equal to negative time derivative of the magnetic field, whatever the magnetic field is. Oh, I better include a direction here, y hat. Okay, so we're almost there, I promise. What we're going to do now is we're just going to integrate both sides with respect to time, dt. So let's write down what that is. So now we have b of t. We only have to concern ourselves with the y component. So b of z and t is going to be equal to negative ik E naught times the integral of this term here, kz minus omega t dt. Okay, so we're going to have to take this integral here. That's going to bring down a negative I omega t. So we get negative ik over negative I omega. It's a nice cancellation. Times E naught times the same kind of form, I kz minus omega t. Use one last little trick here and use the fact that k is equal to omega over c. And that k is going to cancel that out. Remember, this is our fundamental wave relation. I'm just going to write it up here now that we have our solution, in this case. B is equal to B naught, which is going to be E over C, E naught over C times E to the I kz minus omega t in the y hat direction. There's a lot of math. At the end of it, we found that we had k going in the z direction, E going in the x direction, B going in the y direction. So we have this nice fact that E is perpendicular to B as well. Okay. By the way, if you're not super convinced about the generality of this, have no fear. In the assignment 1, you get to prove this in general. It is actually, I would argue, easier to prove it in general. It's one of those cases where it's actually easier to do the general case than the specific case. Because what we did here is we just ground out some integrals in calculus. On the assignment, you just have to use the fact that the cross product between A and B is perpendicular to both A and B. It's kind of a hint. So that's the way you can do it, like in 1 or 2 lines instead of barfing out algebra over a whiteboard. But either way, it works. And we have this very nice fact that E is perpendicular to B is perpendicular to K. All right? And this is true in general. So light is transverse. Furthermore, they both have the same phase factor. They evolve at the same rate. This actually means something. This means that they're minimum at the same time and they're maximum at the same time. So they're in phase and they're mutually perpendicular. So we had this picture. We had this picture from lecture 0. Do you remember that? Of the electric field and the magnetic field propagating away. We know what this is now. We know why it works. We know why it works. Because E is perpendicular to B is perpendicular to K. You can see that here. E and B, which are in phase, they're 0 at the same time, they're maximum at the same time, and they're all mutually perpendicular. And what we see here is that kind of that dance that we were talking about a couple of lectures ago, that the electric field is pulling out the magnetic field, which pulls out the electric field, and they pull themselves back in, and they pull themselves back out, and they kind of propagate through space this way. And that's what light really is. Due to Maxwell's equations, we can see this relation, and that's what this picture is really showing here. Okay, so it turns out we don't even have to worry about the directions of the fields anymore. Because E and B and K are all mutually perpendicular, we only really need to specify one of them. And the convention often is to specify K. That is what we have when we're talking about rays. Okay? When you see optics that look like that, you have these rays of light, right? This is what we're actually talking about now. We're talking about K vectors. But that's going to be next week. So let's summarize. This has been a busy week. We've done a lot of material. Let's summarize what we've done this lecture. So first of all, we can look at a fundamental solution for the electromagnetic wave equation. And it looks like in 3 dimensions, the extension of what you'd expect in 1 dimension for a sinusoidal wave. So we can write it as a complex exponential, as we've done here, or a cosine wave or a sine wave. Generally, we prefer the complex exponential because it's just much nicer to work with mathematically. There's some terms in here which we understood. We have the wave vector, It is the direction that the light goes. The magnitude is equal to 2 pi over the wavelength. That wavelength is given by lambda. And we have the frequency, the angular frequency of the wave is related to the wave vector via omega is equal to ck. This is actually called the dispersion relation, and we'll talk about that when we talk about dispersion in a few weeks. Last important point is that E, K, and B are all mutually perpendicular, and they're in phase. Rather, E and B are in phase. So that is it. We've studied plane waves. Every other wave we use in this course can be built up from mini plane waves. So we've crossed a huge hump here, and we can start using these next week to greatly simplify things and look at optics in a more conventional way. So we'll see you then.